In this video, we will discuss the cases when the events are independent and also how to handle conditionals and independent events. Alright, so if two events are independent, then that means that the conditional probability between the two events is not affected by the occurrence of the previous event. So that can be seen here, the probability of A given B. So if the two events are independent, then B is not going to affect the probability of A. Therefore, that conditional probability is equal to the probability of A. Same thing will happen because if they are independent, then B given A, it's equal to the probability of B if they are independent. Therefore, we can get this expression here, that the probability of A intersection B, it's equal to the probability of A times the probability of B. So this simplifies our calculations if we have independent events. So this will make our life easier a little bit more because the calculations are faster. Okay, so let's talk about the multiplicative rule. This is just a general rule in how to compute intersections when we have conditional events. So in the first case, we have A intersection B. So this is equivalent to the probability of A times probability of B given A. So I don't want you to memorize this probability. This comes from the conditional probability. Remember, in the previous video, we said that the probability of B given A, it's equal to the probability of A intersection B, or B intersection A is the same, over the probability of A, right? So if you solve for the intersection, then you get that the probability of A intersection B is equal to the probability of A times the probability of B given A, right? This is the expression that you're getting here. So same thing, if you change the conditional, then you will get the same expression. All right, so now if they are independent, as we just covered in the previous slide, then you know that the intersection of two independent events, the probability is just the multiplication of the two probabilities. That's because they are independent. So the conditional probability is not like in the previous expression. We get rid of the previous event. So as I said, it's easier to estimate probability when the events are independent. Let's check this first example. So suppose that we have a fuse box containing 20 fuses, of which 5 are defective. If 2 fuses are selected at random and removed from the box in succession without replacing the first, what is the probability that both fuses are defective? So let's first define a couple of events. So remember that we pick first one fuse. So the first event here is that the first fuse is defective, because the question is about both fuses are defective. So first fuse is defective, and event B is that the second fuse is defective. So we're being asked what's the probability that both fuses, so both events happen at the same time. That's the probability of A intersection B, right? So according to the multiplicative rule, this will be probability of B given A. So this is the second fuse is defective given that the first one is defective, times the first fuse is defective, right? So let's find the probabilities. What's the probability that the first fuse is going to be defective? So there are 20 fuses in total and 5 are defective. So if you pick one randomly, That means that the probability of you getting the first fuse effective is 5/20, right? Now, what is the conditional probability? The probability that the second fuse is effective given that the first one was defective, right? Given that, that's the conditional probability. So since we know that the first one was defective, then there are only 4 defective fuses left, right? Initially we had 4, but the first one that was picked was defective, right? Therefore, event B, if the event happens, then there are only 4 defective fuses left, right? So 4 divided by 19. Why 19? Because already the first in the first trial, in the first event, 1 fuse was selected, right? Therefore, this probability is 1/19. It's 1/19. All right, let's check a more interesting example. So one bag contains 4 white balls and 3 black balls, and a second bag contains 3 white balls and 5 black balls. One ball is drawn from the first bag and placed on scene. We don't know if it was black or white in the second bag. Now, what's the probability that a ball now drawn from the second bag is black? So let's represent the problem here. So in the first bag we have 4 white and 3 black. And in the second bag, initially we have 3 whites and 5 blacks, right? So the question here is what the probability that a ball that is taken from the second bag is gonna be black. That's the question here. However, there is a previous event. Remember that one ball is taken from the first bag and we don't know which color it is, right? So we need to account for the 2 possibilities. Therefore, I'm going to define the events. So from the first part, we have 2 options, or there are 2 scenarios. In one is that they take black ball from bag 1, that's the first scenario, right? Or the other possibility is that that's a white ball, right? That is taken from the first one and placed in the second bag. So it's pick a white ball from bag 1. And then there is a second event, right? And that's the question here. It's like B2, it's to pick a black ball from bag 2. Then there are 2 ways in which we can get a black ball at the end. First, that in the first movement a black ball is taken, or maybe if a white ball is taken, then either way the probability is going to be slightly different. So we need to account for the 2 different paths. Then if we want to write it down as an expression, so this will be something as that the probability of B1 intersection B2. So that means the probability that the first ball that is taken is black, and then the second ball that it is taken from the second bag is black too, right? But there is a second option. This is a union, or it's a sum, and it's when the probability of the intersection that the first ball that is taken from the first bag is white, intersection B2. So that's the expression that we need to find. That's the expression that we need to compute here. Alright, so the first one, that intersection, B1 intersection B2, that's equivalent to the probability of B1, so a black ball is taken, times the probability that a black ball is taken from the second bag, given that the first one was black, right? So given B1. So this is the multiplicative rule right there. Plus, same idea here, but now the first event is that a white ball is taken from the first bag, times the probability that a black ball is taken, given that a white ball is taken from the first bag. So these conditional probabilities are needed because the probability is affected. Remember, because if you add an extra black ball here, that will change the number of blacks in the second bag. Or if you place one white ball, that will change the number of white balls in total in that second bag. So that's why it is a conditional probability. All right. So now we just need to plug in the numbers. So which numbers? Let's find the probability. So what's the probability that of B1? The probability of B1 is the probability of getting a black ball from the first bag. So there are in total 3 black balls, right? Out of 7. There are 7 in total. 4 plus 3, 7. So that's the probability of getting a black ball from the first bag. Times, and now the conditional probability, getting a black ball from the second bag, given that a black ball was taken from the first bag. So if that happens, then we will have here 6 black balls. Initially we had 5, but if we add in one more black ball, then there are 6 in total. So that will be 6 over 9, right? Because we're adding that additional ball. Plus, so now we do the same thing, but for the other scenario, when the first ball that is taken is a white ball. So what's the probability of getting a white ball? There are 4 white balls in the first bag out of 7. So that will be 4 over 7, right? Just as we did with the previous scenario, but now this is for the white case. So this is 4 out of 7. Now the conditional probability, since the number of black balls will remain the same in the second bag, so then it's 5 over 9. Remains the same because we're adding a white ball, right? That's what is occurring in the first movement. So that's how you get the desired probability, right? So you just multiply and add them up, you will get that the probability is 38 over 63. Here you have the same problem, but with a different representation. So you have the both bags, and then you know all the expressions that we used in the previous explanation. Alright, so the multiplicative rule can be generalized. So far we have been using the multiplicative rule only for when we have 2 events, but it is possible to have up to k events. So if you want to compute the probability of A1 intersection A2 intersection up to intersection AK, then that's equal to the probability of the first event times of the probability of the second event given the first one, so given the occurrence of the previous one, times the probability of the third event given the intersection of the 2 previous events. So you keep going until the last one is the probability of the last event given the intersection of all of the previous events from A1 up to AK minus 1. So that's the general multiplicative rule. And if we are lucky and the events are independent, then this will be just the multiplication of the individual probabilities. We don't have the conditionals. We get rid of the conditionals in that case. Because remember that if events are independent to each other, then they are not affected by the occurrence of the other event. Okay, let's check this example. It says that 3 cards are drawn in succession without replacement from an ordinary deck of playing cards. Find the probability that the event A1, A2, A3 occurs. And here we have the definition of the events. A1 is the event that the first card is a red ace. A2 is the event that the second card is a 10 or a jack, and A3 is the event that the third card is greater than 3 but less than 7. Okay, so we're being asked to compute the probability of A1 intersection A2 intersection A3. So according to the multiplicative rule, this is equal to the probability of the occurrence of the first event, A1, times the probability of the occurrence of the second one given that the first one has occurred, times the probability that the third one, A3, occurs given that the intersection of the previous two events has occurred. So that's A1 intersection A2. Right? So let's do the first one, probability of A1. Remember that A1 is that the first card is a red ace. So how many red aces you will find in a deck of cards? There are 2, right? 2 red aces. And there are 52 cards in a deck. Therefore, this is probability of A1. It's equal to 2 divided by 52. Then the probability of A2 given A1. What is A2? A2 is that the second card is a 10 or a jack. So there are 4 10s and there are 4 jacks in the deck. Therefore, in total, there are 8 points that satisfy that condition. So that probability is going to be 8. But now this is conditional because we have taken one card, right? So this is divided by 51. Times now the occurrence of the third event given the previous 2 events. The third event is that the third card is greater than 3 but less than 7. That means that the card is a 4, 5, or 6, right? So that then times 4, we have 12 possibilities. So this will be 12 divided by 50. Why 50? Because this is the third card, right? So we started with 52, then we had 51, and now we have 50 available when the third is going to be selected. That means that the probability here is 8 over 5,525. And that will be a solution using the multiplicative rule with multiple events. Okay, this will be the last problem in this video. A town has 2 fire engines operating independently. The probability that a specific engine is available when needed is 0.96. So the probability that engine 1 is going to be working is 0.96, and the probability that engine 2 is working is the same, right? 0.96. The first question is A. What's the probability that neither is available when needed? So what's the probability that they won't be working, right? So A. What being asked here is the probability that E1 is not working, right? That's the complement of E1. Intersection, because at the same time that E2 is not working either, right? So we know that they are independent, right? Because we're told that in the problem. They are operating independently. That means that the probability that one is working is not being affected by the other one. Therefore, if we use the multiplicative rule, this is just, since they are independent, so this is just E1 complement times the probability of E2 complement, right? If you know the probability of E1, the complement is just 1 minus that. And same thing for E2. So this is 1 minus 0.96 times 1 minus 0.96, and that's it. That's how you get the probability in part A. Now in part B is what's the probability that a fire engine is available when needed. What's the probability that a fire engine is available when needed? That means that what's the probability that E1 is going to be working, or E2 is going to be working, or both of them are working. So guys, that probability right there, that's the union of E1, E2, meaning that one will be working or the other one or both of them. So we want to find the union. Probability of E1 union E2, meaning both are working or only one of them is working. So you can solve this part in several ways. You can just do 1 minus the previous 1 minus part A, and that's gonna be it. Or we use the equation. Remember the equation here? Probability of E1 plus probability of E2 minus the intersection. Probability of E1 intersection E2, even though it's not mentioned this intersection, since they are independent, it's just the multiplication, right? So you just plug in the values. So this is 0.96 plus 0.96 minus the multiplication. This is 0.96 times 0.96 or 0.96 square. Therefore, you get the probability that at least one engine will be working. That will be 0.9984, and that will be the solution. Okay guys, I'll see you in the next video.